Hello everyone. Do some music. Auto range profiling. This is one of a sample for CUDA profiling. So CUDA is a tool from NVIDIA that is used for GPU kernel profiling. So it's one of the tools, and it gives you access to a lot of APIs that can help you profile different kinds of metrics when you run a CUDA kernel on NVIDIA hardware. So yeah, this is one of the samples. So let's quickly read through it, see what's happening here, right? So then we'll use the same concept in one of our kernels and we'll see how it goes. Okay, pretty much CUDA runtime, all of these headers. So we'll import those first. WAP average. Okay, so this is the metric. I'm just trying to check what it exactly means. Which one was it? Did I open this? Okay. The average number of WAPs launched overall streaming multiprocessor schedulers. Okay. Let me change the music. So yeah, let's go back to the code. So global void, right? So when we talk about global, it takes it as a kernel. So So this is vector addition kernel. You have pointers to two integer vectors. This is for the result. This is numbers, the size. So block dimension, block index, thread index. You get I. We'll check if I is less than n. Add them. Okay, pretty simple. There has to something similar for vector subtraction. This is initializing the vectors, so you give it a vector n, iterates till n like 0 to less than n, and assigns the value of I to the vector. Cleanup. So basically you're freeing the memory that is assigned to all the pointers. Okay, free device memory. This is host. So this is the CPU memory, so we are just freeing it. For the device memory, we call this runtime API call CUDA free and give the pointer. If it's not freed, it checks and then basically frees the memory. So do vector add and subtract. Just a second. Whoosh. Welcome back. Okay, so let's continue. We have this function call, so do vector add and subtract. Let's see what's going on here. So we have, I'm checking the documentation right now. Hey bro. Trying to run some kernels. So we have two of these kernel calls. So we have the cleanup now. Let's go through this code now. So for the host CPU machine, we have these two pointers will have the address to the main vectors that we want to add. This would be for the result. This is the threads, number of threads per block. So we will give this when we launch the kernel, and blocks per grid. So number of blocks that we want in a given grid, right? So we will need this when we launch the kernel. So right now let's give it 0, and is the size, and since it's integer, this is the total size. So yeah, let's assign memory to it first. So we'll assign it to in the CPU first. So it's malloc, we'll use malloc. First we assign the space in CPU, then we move that data to the host device, right? So device is the GPU, host is the CPU. So we allocate that. We also do the same, but we use CUDA malloc this time. And yeah, the size and everything remains same because it's literally the same vector, right? We just assign those, we create that in the CPU first, then move the whole thing to the GPU. Initialize, we saw this function earlier, so we have it here. It basically iterates and assigns the value of I in the loop to the vector element. So threads per block. So as we discussed, right, we need this value when we launch the kernel, right? So if you see this, so every time you see this is where the kernel is launching, right? So it's basically similar to a normal C++ function call, but then the only thing that's different is this. So you have this blocks per grid and threads per block. So we have 256 threads per block, blocks per grid, and plus threads per block minus 1 divided by threads per block. So let me take my pen. And it's 50,000. So this is approximately 196 blocks per grid. So we'll run this. So last time I tried, there was some issue in the makefile of this kernel, so in this CUDA code. So I don't know when was this last updated, but yeah, or maybe there's some issue with my machine, but yeah, we can see how it goes. So yeah, we have both of these values. So we will verify what we got after we launch this and this value gets printed. Then we call the CUDA kernels, we give these values, we give the address that we stored, right? So we want the addition in this C vector and the subtraction in this, the final answer, right? So you saw the CUDA kernel, right? So these are the third argument is where we store the results. This is the size, and then yeah, this should give us the results. So this will break it down into multiple threads. All of these will take one element, let's say one operation each, and we'll call these kernels one basically subtraction and addition, and then yeah, you'll get the results. So now let's go through this. So this is where we'll be going to the documentation multiple times, because this is the profiling part. So we'll see all these APIs and what they're doing. So this is basically CUDA, so it's NVIDIA's tool. So let me open the documentation. Just give me 1 second. So I'm trying to find the current version. And okay, let me close this. And we have, like, I have some blogs. I mean, I've read them, but if you all want, we can. There's another one. Where is it? So this is the one I was talking to you about, the CUDA. So we want 12.4. Okay, let's close this. Let's go to usage. So we will be using this first. So this is the one code that I have open right now. Auto range profiling. So basically auto range profiling detects the range. So when you launch a kernel, you don't have to set the range, like, okay, this is where my code profiling should start, right? So it will automatically detect the kernel and start your profiling in that range, right? Because it's a normal code and then in between you have kernels, right? Then there's a different mode for range profiling, which is called user replay. So here they also, yeah, before that, right? So what happens is your profiling results get stored in certain counters, right? So counters as in like the hardware counters, right? So if you are collecting multiple metrics for a given kernel, right, but you have limited number of counters, right, so you cannot store all of them at once. So what happens is it does multiple passes of the same kernel, multiple executions, replays the same kernel, and then every time it tries to collect some of the metrics, right, whatever can be covered, like whatever can be stored in the counters. So yeah, I mean, but that if you want, especially like in my case, like if I want something, if I want, let's say, a given metric, and accuracy is really important to me. In that case, I think like if you replay the given kernel multiple times, I don't know how what's the variation, but because this is this is what is internally used by all their tools as well, like Nsight Compute, NSYS, all of these, right? NVProf. So this should be pretty accurate. So even for multiple replays of the same kernel, ideally the result should not vary that much. But once we have this running, like we can maybe test it, right? Like if there's any variation. So yeah, I have this. There's another blog which is like simple CUDA introduction. So we can go through that. Okay, I don't know if I closed it or what. Where did it go? Yeah, this one. So this is not that big. So let me close some of my Chrome tabs because I have a lot of tabs open and it's taking up a lot of RAM. Okay. So we can quickly go through. Let me see the audio. Okay. So yeah, quick comparison between CUDA and C. As you see, literally almost everything is same, right? The only difference is this keyword. And as I showed you in the kernel method, when we're going through the script, you have something like this, right? So that's the only difference. You'll see this in a lot of places. If you see this, that means it's a CUDA kernel, right? So the global specifier indicates a function that runs on the device. As I said, host, CPU, device, GPU. Such functions can be called through host code, because when you run the code, it first runs on the host, that is the CPU, right? The main function in the example is also known as kernels here. So you can call these, like import kernels from a different let's say some header, right, or external method, and then even call that inside, let's say main. even that is called kernel. When a kernel is called, its execution configuration is provided through, we saw this, threads and blocks. In CUDA, it's called kernel launch. NVCC is the compiler that NVIDIA gives to compile CUDA code. Right, so the extension for the code is CU. Right, this is the output where when you run this, the output would be stored in this file with this name. Yeah, so every GPU that you have, right? So all of the GPUs belong to a certain generation and they have something called compute capability, right? CC. So different GPUs have those number different, so you need that CC value when you compile a code, right? Compile a CUDA kernel. So the GPU that I have is 3070 Ti. So the compute capability of that is 8.6. So 8.6, but when you write it in the script, you put it as 86, SM_20, right? So I'll put something like SM_86. So you can get it from the documentation. You can just search your GPU name and it will give you like, then there's an NVIDIA documentation page. It will give you the compute capability of a GPU. So yeah, I mean, this is something similar, right? What we saw. But I mean, we can go through this. CUDA hello world example does nothing. Even if the program is compiled, nothing will show up on the screen. To get things in there, we'll look at vector addition. You define value of n. Vector addition, output, pointer, a, b, n. Right? Basically, a loop through n, add, assign it to the output vector. Now, similarly, right? You allocate memory. Malloc is initially for the CPU machine, right? The host. You do that, you initialize it, then you call the kernel. You call the method, right? So this is like a normal C code, C or C++ code in a host machine, right? How we usually do. Now let's convert it into a CUDA kernel. Change the extension to CU. Convert vector add to GPU kernel. You add this keyword, right? When you call it, when you launch the kernel, this is how you call it. You compile it. See, I think it should be CU here. So yeah, I think that's that. It's pretty simple and straightforward. You get the output in this file, then you can run that, right? The executable after compiling. So you'll notice that program does not work correctly. The reason is CPU and GPU are separate entities. So here they did not move. So you allocated it, but it's still on the host, right? So you have to move it like we saw here. Something like this, right? So let's see. Memory space, yes, CPU cannot directly access GPU memory and vice versa. In CUDA terminology, CPU memory is called host memory, GPU is pointers to CPU and GPU are called host pointer and device pointer respectively. For data to be accessible by GPU, it must be present in the device memory. CUDA driver APIs for creating device memory. Okay, yeah. Allocate host memory and initialize host data. We did that. We have to do that. We have to do this as well. We missed this. We did this. We have to do that as well, because once you have all the operations performed on the GPU, again you have to move it back to the host, right? So let's see the changes that we have to do. CUDA provides several functions for allocating device memory. The most common ones are CUDA malloc and CUDA free. So you have to free the garbage yourself. But that's why you have to free. When you are done, you have to free the pointers that you use, right? CUDA malloc, you give the location size. Yeah, when you're freeing, just give the pointer. CUDA malloc allocates size of count in the device memory and updates the device pointer to the allocated memory. CUDA free deallocates the region of the device memory where the device pointer runs to. They are comparable to, yeah. I think, yeah, that's straightforward. Memory transfer. So first thing is you create a memory block on the CPU. You assign or initialize values there, right? You move those to, then you assign similar memory, like same size memory on the device. Then you move from the host to the device, right? The vectors, like, or whatever data you want to operate on. You do the operations on the GPU, that is the device, and then again move it back to the host, because that's where the final, like, you'll store the data, right? So let's see how to do that memory transfer, right? So we assign the memory in the device. Now we'll transfer the data. So transferring data between host and device can be done through CUDA mem copy function, which is similar to, yeah. So just this is the word that's added, right? So it's similar to what we have in C. The syntax of CUDA mem copy is as follow: destination, source, size, and you have to do this like this so there are two types of operations, right? One is from the device to the host, one is the host to the device, right? So this is CUDA mem copy kind. So you will give the kind of transfer. So we are doing from host to device, right? So I think, okay, yeah, here it's host to device and device to host. So this is what we are going to do first, right? Once we are done with all the operations, we will be doing device to host. Okay. So there are the possible values. We will not touch them as tutorials. Yeah, I mean, we don't need it right now. So for now, these are the two kinds, right? The argument that you'll pass for Yeah, you see this. So this is their code. I downloaded it from the link that was given there. So here here they give DA, which is the device pointer, and just B. And here they give TB, right? So this is the right way, not that. So what we can do is, let's execute this. Just give me 1 second. Oh shit, I was on mute. Okay, we are back. So what I'm going to do is, we have the code now, right, for the vector addition. Let's compile that bad boy. Right, so who uses calculator in a, like, PC? Boomers. Let's open the okay, so we ran the CUDA code for vector addition. This is the compile output file. If you see it here, we have it. Right, so let's run it. What is time? So this is the time that it gave, and this is the output value. So let's see. While initializing, I don't want time. Let's just execute it without that, right? So okay. Okay, let's print addition. We copy it back from device to the host, the output, right? So yeah, I mean, it's 1 and 2, so it should give you 3. Let's change some values there. Idea, this should give the same. Yeah, because literally all the whole vector is 1 for this, 2 for this, so all the elements in the output would be 3, right? So passed. Okay, yeah, I mean, it's addition, right? What else do you expect? Using time does not give much information. Provides a command line profile error called nvprof, which give a more insight information of CUDA program performance. To profile our vector addition, use following command. What am I doing? Okay, nvprof, right? Okay, as I said, My compute capability is 8.6. Is not supported devices with compute capability 8 and higher. Use NSS for GPU tracing and CPU sampling, and NVIDIA Insight Compute for okay. Let me see. I think NCU would not be. I need the whole path, which I don't remember. Okay, I think it's okay, but no, clear, right? Okay, I don't want it to run it here. Anyways, let's try that. I think it needs permission. We want the environment variables, so NCU. But then, yeah, it will have an issue when I run NCU, right? NCU is basically the NVIDIA, what they're talking about here, right? This tool, NVIDIA Insight Compute. So NCU is short for that. So when I run NCU directly, it runs the local version, as in for the one that I have in my user specific storage, right? But it needs certain permission, like admin access to profile. So I need to pass it with sudo, and then when I do that, the NCU version that it takes is different than the local one. So I think this will cause issue, but let's run it and check. And yeah, it needs certain metrics flags as well. So I think I should have it here. Let me go back. I think I have it here. So I have all the commands that I ran. Something like this. Okay, nice. See, I'm genius. But I know that I won't remember it, so that's why I had all these commands saved. So I have the self-realization that I'm not smart. Maybe that's why I'm smart. I don't know. Factor add. Target processes. We want to check for all the processes. This is the part that I was talking to you about. So this is in user, right? It's the root NCU. Let's see. Let's run this. You see, it's running. This is the process. Nice. Do you guys want to see how it looks like when we visualize this? We can do that as well. Let me open my who's watching right now? There's one viewer. Is it me? I don't know. I don't have it open. I think it takes one by default. Am I too close to the mouse of mic? What? Okay, so we have this and we profile the result, right? So this is what we got after we run NVIDIA Insight. Bro, glows. How do you pronounce glows, right? I think I forgot. What's up, bro? So we have so we were trying to run the kernel and trying to profile it using nvprof, but then as it gave the error, right? Like we cannot profile, like it's not available for GPUs with compute capabilities more than 8. So that's why it didn't work for us. Then we shifted to it basically suggested like use Insight Compute, right? So we shifted to that. This is the command and it gave us some result, right? So we have the results here of all the profiling, but it's not that easy to like visualize and like basically analyze, right? So it's on the command line because this is a lot of information. So there is a better way of doing that, which is this thing, this boy, this guy, this dude, this whatever, right? we will generate a report from this, like the same results but in a report format. Then we will import it on your local or like whatever, right, some machine. You can have install this thing and import the report that we generate, that we will generate, and then we will analyze that. So let's see, let's go back to the commands. Okay, this flag. All right. Oh, why did the music stop? Yes, I am watching YouTube. Please don't pause it anymore. So we will add this. So similarly, like whatever last command we ran, right, what we'll do is just add another flag and then we are good to go. So after target process is all, just put output and the report name, right? So // report dummy right. So we got this file generated. Let's download this. Now let's import it with the tool thing that I showed you. So let's see if the drag and drop works. Oh yeah, it works. Okay, so this gives you a lot of information. First thing is, this is the function name. We saw this, right? This is the declaration kind of, right, with the argument data types, duration, compute throughput, memory throughput. So all of these values, like what do they mean? So you can see that as well. So you can just hover over this and it will give you what this means, right? So yeah, we won't spend a lot of time here, but if you want, you can do that. So you can just go to this drop down, you can get different whatever information you need, right? So this should help you in the analysis. This was not that convenient when you run this tool and get the output on the console. So I would highly recommend you to use this tool, generate a report, and then do analysis. It gives you like different kinds of estimations, how much of the resources your GPU kernel is using, and then what are the kind of improvements that can be done, right? Or if there is even room for improvement. So all of that you can use this for. So this is like all the metrics after running the kernel. So the first one that we saw was polished version of this. This one is the raw, whatever you get from the kernel, right? Hardware. So this is that. What else? This is the information of the machine that we have. This is all the flags in the hardware. This is all throughput. So as I said, you can hover over any of the metric and it gives you more information, right? So if you want that, you can do that. Occupancy. So this is the occupancy. So this is the local speed up. So you can take actions based on these analysis reports generated on using Insight Compute to maximize the throughput that you get from the hardware, right? So yeah, you have the option. So yeah, you can copy this image, share it with anyone that you want. But why would you do that? I mean, why not? I do that, but I'm weird. Okay, let me close this. What were we doing? Okay, I mean, yeah, we got this, right? So we saw an example of a kernel, what it looks like, how to profile it, right from the beginning. So you would be able to detect or differentiate a CUDA code from C code. Now you should be able to compile it, run it, profile it, like, right? I mean, so yeah, we saw all of that. There is another tutorial, so we can go through that. So, yeah, I haven't seen this one, but let's go through this. CUDA user kernel execution configuration. We saw this, right? So every time you see this, it's a CUDA kernel. CUDA runtime, how many threads to launch on GPU, right? CUDA organizes threads into a group called thread block. This is very important. You will keep on hearing these three terms: thread, block, and grid, time and time again, right? So please don't get confused. We covered this in one of the last streams. So yeah, if you're not sure what it means. Let's continue to tell CUDA runtime how many threads to launch on GPU. CUDA organizes threads into a group called thread block. A block of threads is called thread block. Kernel can launch multiple thread blocks organized into grid, right? A group of blocks is called grid. All right. The syntax of kernel execution configuration is M, T, M and T, right? So when you launch a kernel, after the name of the kernel method, you give this M and T, which indicate that a kernel launches with a grid of M thread blocks. Each thread block has T parallel threads. So we saw this in the code example, right? So if you multiply this into this, you will get a total number of threads. Because one block has these many threads and there are these many blocks. So blocks into threads per blocks, you get threads. Pretty simple, right? Like, let's see this. This exercise, we will parallelize vector addition from using a thread. You see, last time we kept both the number of threads and block 1, so it was like a single threaded execution, right? So we have the time for that, we have the report for that, so we can update this code, parallelize it, and then compare the analysis, profiling results, right? So this thread will parallelize vector addition from thread block with 256 threads, right? Let me drink some water. Hello. 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 We want to update parallelize into multiple threads, basically 256 threads, the code that we saw right a while ago. So the vector addition one. So if you see this code, this is the kernel being called and it's 1,1. Right, so number of threads per block and blocks per grid are 1 and 1. So it's like a single threaded operation, right? M comma T. Number of blocks per grid. T is number of threads per block. CUDA provides built-in variables for accessing thread information. In this exercise, we will use two of them, thread index X and block index X. So you have, imagine it like this. So you have multiple boxes stacked on top of each other in, let's say, a rectangle or a square or any four-sided quadrilateral, right? But I mean, it has to be a rectangle. Yes, so let's say you have that. Now you have multiple blocks, right? So it's like a Lego, I don't know, small cubes stacked on top of each other, right? And those cubes are called blocks, right? Makes sense. Blocks, cubes, same thing, right? And each of those blocks have multiple threads, right? So each of those blocks stacked on top of each other and side by side will have multiple threads, right? So number of those boxes is this value. Okay, this is the number of blocks per grid. So that whole collective figure that we said, like the whole bigger rectangle, is the grid. That grid has multiple of these cubes, which is the blocks, and then the threads inside them is the the threads inside them is the thread, right? So okay, now let's say you want the location of a thread in a given cube or in a given block of that whole rectangle, right? Somewhere in between, let's say. So each of those blocks have a certain index to identify, right? Let's say 1 2 3 4 5 6 7 8 9 10 11 12 13, right? That number is the block index, so that takes you to that block. So if I say that I want the address of this thread in this box, I point to a given box, right? So what the first step is going to that box, right? Let me reach to that box. After that, in this block there are multiple threads. Now let's go and find that thread. But the first step is finding that actual block, right? So how do you get that? You get it with this. So this block dimension dot x will give you the block dimension, and then thread index will give you a thread index inside that, right? So as I said, so CUDA provides built-in for exit thread information. So this is also called block index. So they haven't mentioned that here, but I think, yeah, because here it's just one block, we don't need that, right? But ideally it won't be the case. Like ideally here you will also have like a bigger value, Here, because it's just one block, we know it starts from, let's say, index, right, 0. So yeah, that's why you're not taking that, or else you'll have a third row here which will give you block index. So you multiply block index, block dimension, and then you add this. So block dimension is basically number of thread, right, size of the thread block. So yeah, I think it's pretty straightforward. The value of thread index ranges from 0 to 5. Value of block index is 250. Block dimension. Oh, sorry. Block dimension is 256 because this is number of blocks, and then this is number of threads in that block. So it's 256. Oh yeah. Oh, yeah. I mean, I was correct. Sorry. Yeah. Sorry for being correct. What I said was block index, which is missing. Which is obviously missing. It's the same, right? So. Parallelizing data recalls a kind of single thread version. We modified a bit to make the explanation easier. What did they modify? Open the code. Output ABN. Output ABN. Okay, we have that. We have index and stride. Stride is 1. So basically the same thing. What else? Index is 0. I mean, yeah, there's nothing. Okay. Right now, we want increment by 1 and start from 0. So yeah, we don't need to change much. In this implementation, only one thread computes vector addition by iterating through the whole array. With 253 threads, the addition can be spread across 2 threads and computed simultaneously, right? So for the kth thread, the loop starts from the kth element. Let's say for the 1, 2, 3, 4, 5. Let's say this is 5, right? So for the 5th thread, the loop starts from 5th element and iterates through the array with a loop stride of 256. In the 0th iteration, the k thread computes the addition of kth element. Yeah. In the next iteration, the kth thread computes the addition of okay, wait a second. Let me print size of float. Let's compile this. Compile. What? ASMR. Size of float equals to 4. But this 32, right? So let's go back to the blog. In this implementation, only one thread computes vector addition. Only one thread. By iterating through the whole array. With 256 threads, the addition can be spread across threads simultaneously. Let's try to read this again. I didn't get it the first time. For the kth thread, the loop starts from the kth element. Why this? That's what I'm trying to understand. Let's say if it's the fifth thread, right? The loop starts from fifth element. Like, why? These are blocks, okay. Each of these colors that you see are blocks, individual blocks. Each of their dimension is 256, right? So each of them have 256 threads. Now, we saw that in the first implementation, the block was just one. Right, so it would only be this one, 0th. So it's sequentially 256 threads, right? Implementation. Now, fifth. Okay. In the next iteration, the kth thread computes the addition of k plus 256 minus 256th element. Okay. So basically the stride is equals to how many threads you have to skip, which makes sense, right? If you are taking the second thread here, if you add 256, you will find the second thread here and vice versa, right? So yeah, let's say if you want to find address of this element, right? So what you do is, as we talked about, right, take the block index here, because you just have one block, it will be just this 0, but then 2 into this dimension, right? So 250, 512, and this one we wanted, right? So 514, 515, 515th element, right? So you can find that block dimension into block index plus thread index, right? Yes. So I don't know what is this afterwards. Let's read. In this exercise, we'll parallelize vector addition from tutorial 1 using a thread block with 2 threads. Yeah, I mean, right now we won't be doing that, but it's pretty straightforward, right? So let's see the other one. CUDA GPUs have several parallel processors called streaming multiprocessors or SM. Yep, we have talked about this in the past streams. Each SM consists of multiple parallel processors and can run multiple concurrent thread blocks. To make advantage of GPU kernels, kernel should launch multiple thread blocks. This expanded. Okay. block index. Then you also have grid dimension. Okay. Na, 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 na. Na, na, na. Instead of using a thread block to iterate over the array, we will use multiple thread blocks to create n threads. Each thread processes an element of the arrays. Na, 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 na. So yeah, as I talked about, right? Block index into block dimension plus thread index. You'll get the index of the thread, the current, like the thread that you want. Try to implement this. Yeah, you have to add this as well. Like you have to make sure that the index that you have, the thread index, is at least less than the range that we have set, right? Or it will go out of bounds, so we don't want that. So in all the threads, like in a lot of kernels, in majority of the kernels that code you'll see, you'll find something like this, like I less than n, before going into the logic of the kernel. You see, like one thread, this was the time, one block, multiple blocks, this is the speed up, 1000 times, 1200 times, right? So which is significant. All right, that's it for the tutorial. Okay. So I think, yeah, we have a good idea of, at least like if you have to write a small like CUDA kernel, I think you should be able to do it, right? So the only condition is you should have CUDA, NVCC, all of these things installed in your machine. Once you have that, you are good to go. Seriously, like, yeah, it's pretty simple. It's, if you know C, you know 99% of CUDA. 95, 80. Let's make it 80. I think maybe 90. I don't know. Simple C. I mean, yeah, it's, you can read this if you want. I don't know. Right now, it's just too boring. Well, so yeah, it's a introduction again. We talked about a lot of things. The tutorial already covers that. So yeah, I think it would be the same thing. So what we can do is, first thing, we'll close this. We don't need this. We will close this as well. We don't need this. Right. Now, we have these APIs, right? What I'll do is, let me go take a break, eat something, get a coffee, and then I'll come back. Okay. I think I'm going to stop the stream here for a bit, maybe an hour, and I'll come back. Okay, I think we covered a decent introduction to CUDA, so this should be a right segue to CUDA, right? And as like there, even like I have to learn a lot of things, so it would be slightly slower than this. So yeah, we'll chill, we'll learn, we'll hang out.